In this presentation, we focus on a synchronization problem that quietly determines whether a terminal runs smoothly or collapses into waiting and congestion. Coordinating Quay cranes with yard trucks? Quay cranes are fast, expensive resources, and they create value only when a truck is available to take the container away. Yard trucks are flexible, but they lose efficiency when they queue under cranes or drive to the wrong place at the wrong time. The integrated problem is to schedule both resources together so neither one becomes the bottleneck for the other. The goal is to reduce vessel turnaround time while increasing utilization of cranes and trucks. The hard part is that the two systems are interdependent. Cranes depend on trucks to clear containers, and trucks depend on cranes to release containers. Consider Port Harmony Terminal. It operates 6 Quay cranes along a 1,200-meter berth and uses a fleet of 18 yard trucks serving 4 storage yard blocks. Each incoming vessel requires coordinated unloading of roughly 800 to 1,500 containers, and each crane can handle about 25 to 30 moves per hour under good conditions. The problem is that the terminal is not operating under good coordination. With separate scheduling, cranes often wait for trucks and crane productivity drops from 28 to 18 moves per hour. At the same time, trucks wait for cranes and truck utilization drops from 75% to 45%. On top of that, containers are sometimes staged in suboptimal locations, creating extra repositioning moves. The terminal needs an integrated approach that can coordinate in real time and adapt to variable travel times and disruptions. We solve the integrated Quay crane and yard truck scheduling problem through a tiered toolkit. Tier 1 gives a mixed integer programming model that defines the complete coordination structure and provides an optimal baseline for small instances. Tier 2 uses an earliest deadline first coordination heuristic to deliver fast decisions with high utilization. Tier 3 applies ant colony optimization to search better combinations of crane, truck, and container assignments. Tier 4 uses unsupervised learning with clustering to create container groups and specialized scheduling rules. Tier 5 embeds decisions in a digital twin for what-if analysis and predictive adjustments. Tier 6 moves to autonomous multi-agent coordination with auctions and shared learning. Tier 1 frames the problem as a rigorous optimization model. Each container must be assigned to exactly one Quay crane for handling and exactly one yard truck for transport. The model also includes a 3-way linking concept, so the system can represent a synchronized pairing between a specific crane and a specific truck on a specific container. The objective combines two ideas. First, minimize the overall completion time, meaning the time when the last container is finished. Second, include a distance penalty term so the plan avoids inefficient crane travel and poor spatial decisions that create unnecessary movement. The value of the Tier 1 model is correctness and completeness. It forces all assignments and conflicts to be explicit. This slide defines the objects the model tracks. You have a set of containers to be handled, a set of Quay cranes, a set of yard trucks, and a set of yard locations. Operationally, these sets define the scope of the decision. The plan is not just handle all containers, it is which crane handles which container, which truck transports which container, and where does the container go in the yard, all inside one consistent framework. Parameters describe the physical and operational inputs. You have crane handling times that depend on which crane handles which container. You have truck travel times to specific yard locations. You also have a distance penalty, representing the cost of inefficient spatial assignments. The model also includes each container's yard destination, plus a large constant used to express logical constraints. Operationally, these parameters are what make the optimization meaningful. If travel time, handling time, or distance penalties are inaccurate, the solution can look optimal in a model but perform poorly in the real terminal. Decision variables represent the assignment decisions. One decision indicates whether a container is assigned to a given crane. Another decision indicates whether that container is transported by a given truck. The third decision is the linking concept that captures whether a specific container is executed by a particular crane and truck together. The model also includes the overall completion time variable, which represents the make span. This set of variables is what allows the model to express synchronization explicitly rather than as an afterthought. This slide shows the objective as two parts: minimize makespan plus a weighted distance penalty for inefficient assignments. Operationally, minimizing makespan reduces vessel turnaround time. The distance penalty is there because a plan can sometimes reduce makespan by creating overly long travel patterns or awkward spatial decisions, which can hurt robustness. Combining both terms encourages schedules that are fast and spatially sensible. This constraint enforces that every container is assigned to exactly one crane. Operationally, it prevents two failure modes. The model cannot cheat by leaving a container unassigned, and it cannot assign the same container to multiple cranes. Every container must have one clear handling responsibility. This constraint enforces that every container is assigned to exactly one yard truck. Operationally, this ensures transport responsibility is unambiguous. Without this rule, the model could create vague plans where a container is handled but not transported, which is not executable. This constraint links the three-way coordination concept to the crane and truck assignment decisions. Operationally, it ensures that the system can claim a synchronized crane-truck execution only when the container truly is assigned to that crane and that truck. It prevents inconsistent combinations where the model pretends a crane-truck pair is working together on a container that they are not both assigned to. This is the core coordination rule. It limits conflicts between cranes and trucks by ensuring that a crane and a truck are not simultaneously committed to incompatible work. Operationally, this is what reduces idle time. Without synchronization constraints, you can produce plans where trucks arrive too early and wait under cranes, or cranes finish and wait for trucks. Synchronization forces the plan to coordinate timing and pairing, so both resources are used effectively. This constraint defines the overall completion time in terms of what cranes and trucks must do. The makespan must be large enough to cover handling time and travel time implied by the assignments. Operationally, this makes the schedule realistic. It ensures the model cannot claim a completion time that is shorter than the actual time required for cranes to handle containers and for trucks to move them to the yard. This slide visualizes the integrated structure. Containers are connected to cranes and trucks, and the decision is about matching them in a coordinated way. Use this diagram to see the main story of Tier 1. Instead of optimizing cranes and trucks separately, you choose combinations that work together, which is what prevents waiting on both sides. This example uses 3 containers, 2 cranes, and 2 trucks. Handling times differ by crane and container, with values such as 2 minutes, 3 minutes, and 2.5 minutes. Truck travel times to the yard include about 4 minutes and 3.5 minutes. A representative optimal plan assigns specific containers to specific cranes and trucks and achieves a makespan of 9.5 minutes, described as perfect synchronization. The lesson is that even in a small instance, alignment between crane readiness and truck availability is what drives completion time. Tier 2 focuses on speed and operational deployment. The earliest deadline first idea is to prioritize containers by urgency, then dispatch coordinated crane and truck actions so the most time-critical containers are processed first. The key improvement over naive earliest deadline first is coordination. The heuristic maintains priority queues for cranes and trucks, so it can dispatch them as synchronized pairs. That avoids the common failure mode where cranes chase urgent containers, but trucks are not positioned to support that choice. This flow slide represents the dispatch loop. Containers are prioritized, cranes and trucks are matched, a coordinated assignment is issued, and the system state is updated. Operationally, the update step is essential. Every dispatch changes where trucks are and which cranes are busy, so the priorities and feasible pairings change continuously. The flow emphasizes that coordination is a repeated decision process, not a one-time plan. In this code section, you typically see how container deadlines and handling times are represented and how the initial priority order is computed. Operationally, the core requirement is that priority is recomputed when conditions change. If travel time or crane availability shifts, a container that used to be urgent may no longer be the best next choice given coordination constraints. This section usually covers the matching of cranes and trucks and the feasibility checks that ensure the pair can execute the chosen container next. Operationally, matching is where idle time is won or lost. A good earliest deadline first coordinator will sometimes delay a slightly more urgent container in order to execute another container immediately with a ready crane truck pair, reducing overall waiting and improving throughput. This section typically handles the update logic. Assign the container, update crane and truck availability times, and update queues. Operationally, this update is what keeps the method consistent. If you do not update availability precisely, the schedule becomes unrealistic and you will overbook cranes or trucks. This slide provides a concrete earliest deadline first schedule example. 5 containers have deadlines of 20, 15, 25, 18, and 22 minutes, with handling times such as 3, 2.5, 4, 3.5, and 2 minutes. A representative schedule completes the set with a make span of 22.5 minutes and reported resource utilization of about 95%. The takeaway is that coordinated dispatch can achieve high utilization even with urgency constraints. Tier 3 uses ant colony optimization to search a larger space of crane truck container combinations than a greedy rule can explore. Each ant builds a complete schedule by choosing assignments probabilistically. Pheromones represent learned preferences for certain crane truck combinations on certain containers. Heuristic desirability favors assignments with low combined crane handling time and truck travel time. Over many iterations, the colony concentrates on patterns that reduce make span and improve coordination. This slide visualizes the construction process. Ants traverse the decision graph of container assignments and reinforce successful choices. Operationally, this is learning from experience. If certain pairings repeatedly produce good schedules, pheromones strengthen those choices, making them more likely in future iterations. This slide presents the heuristic desirability measure used in ant colony optimization. The idea is to prefer pairings that have lower combined handling and travel time. Operationally, heuristic desirability is the greedy signal inside the metaheuristic. It guides ants towards sensible choices while pheromones incorporate memory of what worked best overall. This slide shows the probability structure for selecting an assignment based on pheromone strength and heuristic desirability. Operationally, this probability rule is what balances exploration and exploitation. If pheromone dominates too much, the colony converges early and can miss better schedules. If heuristic dominates too much, the method becomes a greedy rule with limited search power. This code section typically initializes pheromones, defines feasible moves, and starts the iteration loop. Operationally, feasibility rules are essential. If infeasible assignments are allowed into the construction process, pheromone learning becomes polluted by schedules that cannot be executed. This section often shows how each ant constructs a schedule step by step and how it updates temporary state such as resource availability. Operationally, state updates ensure that the schedule is consistent in time. Ant colony optimization is not only choosing which resources match, it is also choosing an order that respects availability. This part usually evaluates constructed schedules and computes their cost, such as make span and any penalties. Operationally, evaluation must reflect the real objective. If evaluation ignores waiting or conflicts, pheromone updates will reward the wrong behavior. This section often applies pheromone evaporation and deposition. Evaporation prevents the system from locking into old patterns. Deposition reinforces choices used in high-quality schedules. Operationally, this is what lets the method improve over time and adapt when conditions change. This section typically finalizes the iteration loop and tracks convergence of best and average solutions. Operationally, convergence tracking is a quality gate. It tells you whether the method is actually learning better coordination patterns or just wandering randomly. This slide reports a small example using 20 ants and 100 iterations. It states that the algorithm converges after about 60 iterations. The reported make span is 14.0 minutes, and pheromones are described as clearly favoring the optimal crane truck combinations. The operational takeaway is that learning-based search can discover strong pairings and sequences that a simple greedy rule can miss. Tier 4 introduces unsupervised learning to discover structure in the workload. Instead of treating every container as a unique case, the idea is to cluster containers into groups with similar handling time, distance, and urgency profiles. Clustering supports specialization. For example, fast and urgent containers can be routed through a fast track rule, while slow and far containers can be batch processed to reduce travel overhead. This reduces decision complexity and can increase throughput by matching strategies to container types. This slide shows the clustering pipeline. Represent each container with features such as handling time, yard distance, urgency, weight class, crane accessibility, and bay position. Then cluster and assign strategies. Operationally, the architecture is useful because it turns a high-dimensional scheduling problem into a smaller set of cluster policies. That makes decisions faster and often more stable in practice. In the first code section, you typically see feature extraction and normalization. Operationally, feature scaling matters. If one feature dominates purely because of units, the clusters will not reflect meaningful operational patterns. This section often runs the clustering algorithm and assigns a cluster label to each container. Operationally, cluster labels are not the goal by themselves. The goal is to drive different scheduling behavior for different groups, so the mapping from cluster to strategy must be explicit. This section typically selects strategy rules for each cluster, such as fast track, balanced allocation, or batch processing. Operationally, strategy selection determines whether clustering helps. If all clusters are treated the same, you do not gain value from the segmentation. This section usually executes the cluster-specific scheduling logic. Operationally, this is where specialization becomes real. Certain crane truck pairs are preferred for certain container types, and dispatch rules differ by group. This final code section often reports schedule metrics such as makespan and utilization. Operationally, metrics allow you to validate that clustering is improving performance compared to a uniform rule. This slide reports 12 containers clustered into 3 groups. The fast and urgent group has an average handling time of 2.1 minutes, and urgency about 0.85. The reported overall makespan is 18.2 minutes with about 89% utilization. The takeaway is that specialization by container type can increase utilization while still respecting urgency. Tier 5 uses a digital twin to connect cranes, trucks, containers, and yard infrastructure in a synchronized virtual replica. The twin supports what-if analysis, predictive maintenance, and dynamic reallocation before bottlenecks occur. Operationally, the twin provides a safe space to test scheduling changes and evaluate impacts on vessel turnaround time and utilization without risking live operations. This slide emphasizes the system of systems view. The twin integrates physical sensors, real-time data streaming, simulation, analytics, and decision support. Operationally, a key benefit is consistency. Crane decisions affect yard movements and truck dispatch, so the architecture ensures updates propagate through the system rather than optimizing one subsystem in isolation. This example describes real-time simulation with updates every 5 seconds and about 10,000 events per minute. The twin detects vibration patterns indicating bearing wear in 6 days on Crane 3. The system reduces Crane 3 load by 20% and increases Crane 2 and Crane 4 utilization by 8% each, maintaining productivity at 96% of normal. It avoids a potential 4-hour failure that would have reduced terminal capacity by 15%. Reported benefits include 23% reduction in crane idle time, 18% improvement in truck utilization, and 12% decrease in container dwell time. Tier 6 reframes the system as a set of intelligent agents. Cranes and trucks bid on container tasks based on their state, distance, workload, and predicted efficiency. Operationally, the goal is decentralized coordination without a single dispatcher. Auctions allocate tasks and reputation mechanisms reward reliable behavior. This improves resilience when conditions change rapidly. This slide emphasizes negotiation and emergent coordination. Agents form coalitions and self-optimize schedules through repeated interactions. Operationally, this supports scalability. As the fleet grows, local bidding and negotiation can distribute decision-making load while still producing coordinated global behavior. This slide explains the payment concept in a Vickery-Clark-Groves style auction. Winners pay the second highest bid plus an externality component. Operationally, the point is incentive alignment. Proper payment rules encourage truthful bidding so the system allocates tasks efficiently rather than rewarding strategic manipulation. This slide describes multi-agent reinforcement learning with experience sharing, such as sharing queue table experiences through a gossip protocol. Operationally, experience sharing accelerates learning. If one agent discovers a reliable coordination pattern, that knowledge can spread through the network faster than each agent learning in isolation. This slide gives a concrete example. A vessel arrives with 240 containers, so the system initiates 240 auctions. In one case, a crane and truck coalition wins a container at a price equal to the second highest bid. When one crane agent experiences a communication failure, emergency auctions redistribute work and maintain about 87% of normal throughput. Over 100 vessel operations, specialization emerges, such as a crane becoming 15% faster on heavy containers and a truck reducing travel time by 22% through learned routing. These practice questions reinforce implementation readiness. You practice writing the mixed integer formulation for 4 cranes and 6 trucks, serving 8 containers. You also practice earliest deadline first scheduling with explicit deadlines and colony optimization pheromone evolution over several iterations, clustering-based specialization, digital twin compute sizing for 15,000 events per minute, and multi-agent auctions with fault handling. To close, remember that crane truck synchronization is a primary driver of key productivity and vessel turnaround time. When resources are scheduled independently, you see cranes waiting for trucks and trucks waiting for cranes. Tier 1 provides a complete mathematical specification but scales poorly. Tier 2 provides fast coordinated dispatch. Tier 3 improves solution quality through learned search. Tier 4 creates specialization through clustering. Tier 5 adds prediction and what-if control through a digital twin. Tier 6 adds resilience and scalability through decentralized auctions and shared learning.